The main theorem that I'm going to introduce in this last lecture is the mean value theorem. And to see where it comes from, recall that we have just been looking at Rolle's theorem, which assumes f is continuous on the closed interval ab, differentiable on the open interval ab, and it also assumes that f of a equals f of b. And then that guarantees the existence of some place over that open interval ab where the tangent line has to be horizontal. So in this lecture, we're going to ask the question, what if we drop the condition that f of a has to be equal to f of b? What happens then? So here I've drawn a graph of a function that has different values at its endpoints. And if we go back up to our original Rolle's theorem picture, notice that if I were to draw the secant line between A and B, then it would have the same slope as the tangent line. They would both be horizontal. I have a similar result here. I could draw the secant line that goes through my endpoints. And what this is saying, what the mean value theorem says, is that there has to be a place somewhere in between A and B where the tangent line that you get at that point is parallel to the secant line over the whole interval. So this is a tangent line, and then my lighter blue line is the secant line. Recall that the tangent line is our way of computing the derivative at a point, the slope of that tangent line, and it represents an instantaneous rate of change. It's how the function is changing at a single point in time. Whereas the secant line is an average rate of change. It's computing how your function changes on average over the whole interval between the 2 points that you're drawing the secant line. And so here what we're saying is that there actually has to be a place somewhere in your interval, a place C, where the instantaneous rate of change C is actually equal to the average value of the average rate of change over the whole interval. So the high level of what we've just found here is that there has to exist a C in AB such that the slope of the tangent line at x equals C is equal to the slope of the secant line over the interval AB. So if we write this out as a theorem, it's the mean value theorem. So here, when we say mean value theorem, we're really talking about the average rate of change. We're making a claim that if you look at the average rate of change over your interval, there has to be a single point in time in the middle of that interval at which that instantaneous rate of change is equal to that mean rate of change or average value. And so this says, let f defined on the closed and bounded interval AB be such that f is continuous on the closed interval AB and differentiable on the open interval. So we drop that third condition of Rolle's theorem, and then we get to say that there has to be a C in AB such that f prime of c equals that average rate of change, which is the slope of the secant line. So it's f of b minus f of a over b minus a. So again, we're talking about instantaneous rate of change. And this is at c versus average rate of change over the whole interval AB. Rolle's theorem is just a special case of the mean value theorem where f of a equals f of b, because then when you plug into this top part of your slope here, the average rate of change that you compute is 0. So that's something that's important to note. To prove this, we can actually shift the way that our conditions of the mean value theorem are given in such a way that we show that the hypotheses of Rolle's theorem are met, and then we can apply Rolle's theorem to that shifted function and recover the result of the MVT. So in that way, we can kind of think of the MVT as being a corollary of Rolle's theorem. So our goal is going to be, we know that when you have a function that is continuous on a closed interval, differentiable in the open, and the endpoints take on the same value, then we know there's a place where that derivative is 0. That's Rolle's theorem. So my goal is going to be to find G such that G meets the conditions of Rolle's theorem, and specifically that means what we're going to need to worry about is that G of A needs to be equal to G of B. And the other thing is that we want G prime of C equal to 0, because that's the result we're going to get out of Rolle's theorem. We want that to be equivalent to being able to say that when you rearrange that, G prime of C equal to 0 is really just a rearrangement that shows that F prime of C is equal to F of B minus F of A over B minus A. So what this is saying is that we would really like G prime of C to evaluate to give us F prime of C minus that quantity F of B minus F of A over B minus A. Because then if that's true, then when that's equal to 0, we can rearrange and we have exactly the result we're looking for. So our goal is to figure out what G should be. And just looking at it and using our understanding of antiderivatives, we can probably come up with a good function that we want to test as a candidate for G. So we see that it's going to have to contain the derivative of f. So maybe we want, G of x should be f of x. And then this other thing over here, this is a constant. So we want to subtract off a line with slope f of b minus f of a over b minus a. Well, we have a line like that. Remember, in our picture, that line was exactly the secant line. And it turns out if I take the secant line, if I take the function and I subtract the secant line, because my endpoints take on, because those are intersection points, like the secant line and f have the same values at the endpoints, when I subtract those two functions, I'm going to end up getting 0. So this seems to meet the conditions I'm looking for. If I take g of a, for example, that's going to be f of a minus the value of the secant line at f of a, which is just f of a. So that would be 0, and then you get the same thing if I plugged in b. So we now know we want to use the equation of the secant line, which we know its slope. Its slope is just f of b minus f of a over b minus a. And then we just need a point on the line so that we can use the point slope formula. So I'm just going to select the point at a comma f of a, and that's the equation of the secant line. So this guy is the equation of the secant line. And our claim is that this new function g that we've defined is going to meet the conditions of Rolle's theorem. And once we've shown that it does, we get the fact that g prime of c has to be 0, but we've cleverly defined our g so that when g prime is 0, that really means that f prime has the same value as the secant slope. So that will be our proof. So we're going to assume f is continuous on the closed interval AB and differentiable on the open interval AB. And then we're going to define g of x to be equal to f of x minus that equation of the secant line. Now remember, the first thing that we need to do is make sure that g satisfies the hypotheses of Rolle's theorem. So we need to check continuity on the closed interval, differentiability on the open interval, and we need to make sure that g of a equals g of b. So the first thing we need to assert, why is g continuous? So we can say that g is continuous on this closed interval AB by the ACT, since f and the equation of the secant line are continuous functions. On AB. And then similarly, if I go and I try to compute g, I know that g is differentiable because it's the difference of differentiable functions. So it's differentiable on AB because it is the difference of differentiable functions. What I'm using here is the algebraic differentiability theorem, which we abbreviate ADT. And then the third condition, I know that g of a, remember the way we designed it, because the secant line intersects f at a, if you take the difference of the value of f at a and the secant line at a, you're just going to get 0 because it's an intersection point between those two functions. And the same thing is true at b. Now, you could go through and you could plug a into the formula above that we gave for g, and you could compute it by hand and verify you do get 0, and you can do the same thing for b, but that's not necessary. This is really high level, just using the fact that f intersects the secant line at x equals a and x equals b. So now we've shown that the conditions of Rolle's theorem are met, which means we can say by Rolle's theorem, there exists a C in AB such that G prime of C is 0. But remember how we chose G prime. G prime of C is just F prime of C minus F of B minus F of A over B minus A. And that really implies, when I rearrange, that F prime of C is equal to the value of that secant slope. And that's exactly what we wanted. So this next theorem is going to demonstrate one way that we might apply the mean value theorem to recover a new result. So suppose you have a function and you know that its derivative is always greater than 0 for any x that you select in the reals. We know that from calculus that implies that f is strictly increasing. We've seen this before. This is how we've always thought about the derivative. But you probably didn't prove it in your class when you took calculus. Now, first of all, in order to prove this, we need to make sure we understand what it means to be strictly increasing. That just means that for any inputs, A or B, in R, if A is smaller than B, then f of A should be less than f of B. That's our way of checking that our function is always increasing and going up in size. The inputs and the outputs should be ordered in the same direction. But notice here, I've now sort of given us an idea about maybe to use the mean value theorem because I've introduced this notation of A and B. That's my whole goal, is to prove that for arbitrary A and B, I can get this relationship between f of A and f of B. So my goal is going to be to apply the MVT to the interval AB. So the proof of this is really just going to be direct and sort of follow your nose, so I'm going to start writing it as we talk through it. So we want to assume f prime of x is greater than 0 for all x in R. And then our structure of our proof, which should follow the logical structure of the conclusion. So I am going to be paying attention to this quantified statement for the definition of strictly increasing and follow that in how I introduce my variables. So I'm going to let A and B be in R, such that A is less than B. And then we're going to be considering our function on the closed interval AB, and we're going to try to demonstrate that the conditions of the mean value theorem are met, because that gives us access to the derivative, and that'll give us access to our assumption that the derivative has to be greater than 0 for all x. So I first need to check, that f is continuous on this interval, the closed interval AB, and that it's also differentiable there. Now, technically, we have not been told either of those conditions explicitly, but we have been told that the derivative is greater than 0 for all x. That's implied. That implies that f is differentiable for all x. So since f prime of x is greater than 0 for all x in R, it must be that f is differentiable on R. Because it's implied that f prime of x exists for every real number if it's going to be greater than 0. And by theorem, f must be continuous because we know that differentiable implies continuous on all of R. So in particular, we can say that we have continuity on the closed interval and differentiability on the open interval, AB, because we know we're differentiable and continuous everywhere for any real number. So in particular, f is continuous on the closed interval AB, and f is differentiable on the open interval AB. So then by the MVT, there has to exist a C in AB such that f prime of C is equal to f of B minus f of A over B minus A. But remember our assumption. We assumed that the derivative was always bigger than 0. So since f prime of C is greater than 0, and since B minus A is greater than 0, remember we've assumed A is strictly less than B, it must be that f of B minus f of A is strictly greater than 0. And rearranging, that says f of A is strictly less than f of B. And what we've just done is shown the definition of strictly increasing. That is it for this section.